Okay, today we want to talk about the main reason why free cumulants are a good object in free probability theory, and that's the characterization of freeness. So we can characterize freeness, which was defined in terms of moments, also by cumulants, and the characterization is that it's equivalent to the vanishing of mixed cumulants. And last time, essentially, we saw a special case of this, because one is free from everything. I mean, if this theorem is true, then it has to be that if I have mixed cumulants, which involves 1, which means a cumulant where at least one of the entities is 1, then this should be 0, if at least I have 2 arguments. And that's what we proved last time. Okay, and this will be an ingredient in the proof of the general theorem, so let me start right away with the general theorem. So this is one of the main theorems about free cumulants. And so usually, I mean, we phrase this in a way that saying that freeness is equivalent to the vanishing of mixed cumulants. And of course, the cumulants here are free cumulants. Okay, so this theorem is true to me. So I proved this in almost 25 years ago. Okay, and of course, I mean, this is based somehow on a corresponding theory in a classical context. There are, of course, classical cumulants, which go with all partitions, and there's a corresponding characterization of classical independence. And I mean, this goes back essentially on one side, this description of multiplicative function goes back to Giancarlo Rotta, but then this description of cumulants in these combinatorial terms maybe is due to Terry Sweet. Okay, so there are inspirations from the classical theory, but of course the proof doesn't use anything from this, but we just do it right away. But we could prove the classical theory in the same way. Okay, so what is the sentence? So we have a non-commutative probability space. Non-commutative probability space. And then of course we have corresponding cumulants. They are defined by using phi. So Kn free cumulants. And of course we can extend them multiplicatively to functions on all non-crossing partitions. Okay, now we consider the situation which we have for freeness. So we consider a set of subalgebras of our algebra. So we consider unitary subalgebras. Let's call them AI, indexed by elements from some index set. So those are subalgebras of I. Okay, and then we want to know whether they are free or not. Okay, and then the statement is then following equivalent. And of course, the first is that they are free. Okay, so the first statement is the AIs, or I running over our index sets, are freely independent. And of course, this is the definition. This was the definition of freely independent, was in terms of the moments. Okay, now we are claiming there's an equivalent characterization in terms of the cumulants. And what is this? So that's, okay, what I already said, that's the vanishing of mixed cumulants. So in words, mixed cumulants in subalgebras vanish. Good, but what do I precisely mean with this? So I mean that, okay, I mean there are many situations where cumulants are 0. I mean it's very similar to the definition of freeness. Freeness told there are situations where moments are equal to 0. And here it's very similar, but conditions are somehow better. So namely, what is it? So we consider cumulants. Okay, I want mixed cumulants, so I should have at least 2 arguments. So the number of arguments should be greater than 2. Then I have arguments which come from the subalgebras. So let's say I have A1 up to AN, and AJ comes from one of the subalgebras. Let's say AIJ. j running from 1 up to n, so I consider n arguments. Okay, and then in the case of the moments, we needed that those guys are centered, phi of them is equal to 0, and we needed that they are alternating. So neighboring elements are coming from different subalgebras. And here we have a much bigger requirement, namely centeredness doesn't play a role at all. And this alternating, we can weaken this to just saying that it's mixed, which means we have at least two different subalgebras showing up. But it's not that neighbors have to come from different ones. So we only require that there are at least two indices, let's say L and K, such that the IL is not the same as the IK. So this means IL comes from a different subalgebra than IK. Okay, and when this happens, under such a situation, then it follows that kappa n of the corresponding A's, so kappa n of A, AA1 to AN is equal to 0. Okay, so you see it's quite similar to the definition in terms of moments, but the conditions here, the requirements which I need to get 0 are somehow weaker, which means it's much easier to satisfy them. Maybe at the moment it doesn't look so big a difference, but I mean it's really much better to work with this than this definition in terms of moments. Because there we have the condition they must be centered and they must be alternating. And I mean to somehow to satisfy one of them is easy, but if you satisfy one of them, if you're centering your arguments, you are losing the other one. So satisfying both is somehow not so easy. Okay, so here we don't have this problem. Good. Okay, so let us prove this. So we are claiming those are equivalent, so we should show both directions. And actually the simple direction is, if we have this here, then it satisfies this. I mean, so somehow it's clear that if we would have here the same conditions as for the moments, that those guys are somehow equivalent. I mean, that would be easy, and that will also be part of what we are showing. The point is that we can weaken the assumptions here. Okay, but so let's go from here to here, which is the easy direction. 2, 1. So assume we know that mixed cumulants vanish, and we want to show that our algebras are freely dependent. Okay, so freely dependent means we have to look at moments, there we have our definition. So let's look on the situation which we have there. So consider the situation as a definition for freeness. This means I'm looking on elements, but now I require stronger conditions which I have in the definition. Also, this means I have elements aj, which are in each of them is in one of the subalgebras. But now I also ask that they come alternatingly from different subalgebras. So I1 is different from 2, this one different from IN, and I also want them to be centered. So I also ask that each of them is 0 and phi of aj is equal to 0 for all j running from 1 to n. Good, and then we have to show that phi of the product is equal to 0. That's the definition of freeness. Show phi of 1 to n product is equal to 0. Good, and of course, I mean, we have to go to the cumulants because we know something about cumulants, so we use the relation between moments and cumulants, essentially the definition of the cumulants, written in the other way, that phi is given by summing over cumulants. So let us check this. So if I want to calculate phi of a1 up to an, I can express this cumulants. It's given by summing over all non-crossing partitions. And here I get the kappa pi of my arguments a1 up to an. Kappa pi, what is kappa pi? Kappa pi, of course, is the product of kappas corresponding to the blocks. So this here is the product over the blocks of pi. And for each block, I get a kappa, is the index, the number of elements in the block. And then as arguments, I take the are the A's which are connected by this block. So this by A1 restricted to block B. Okay, and so I have to see this guy is 0. So I have here a sum over many terms. So the best thing is if I could see that each of those terms is 0. So all of them should be 0. Okay, each of them is a product of terms. So it would be good if at least one factor is equal to 0. Okay, and of course, yeah, so I would have to see that at least one of the terms which I have here leads me to a situation of which I know that the kappa is equal to 0. Okay, so what I need here is somehow a mixed cumulant. Okay, and this, maybe not for all blocks I get mixed cumulants, but there is at least one for which I know that this is the case, and this is an interval block. So we know a non-crossing partition has a recursive structure, so namely I find a block which is an interval, which means it only consists of neighboring elements. Then I can take this out and I get again a non-crossing partition. But so at least I have here an interval block, and so for this interval block I have neighboring elements of the A's. So this interval block might be singleton, so it only has one argument, then of course it's not mixed. Okay, but for one argument we get contribution kappa 1, which is the same as phi, and phi is centered on the A's. Okay, so if the interval block is a singleton, then the corresponding factor here vanishes because of the centeredness of the A's. Okay. If it is not the singleton, then I mean it contains at least two elements, so it contains two neighboring A's, but I mean neighbors here are coming from different algebras, so it contains a mixed. It's a mixed cumulant, containing at least two. And our assumption was such guys are 0. Okay, so this means for each partition shown up here, we find at least one interval block, and the factor for this interval block is 0. Either because the A's are centered, or because of the assumption that mixed cumulants are 0. Okay, so here, if the interval block, then this term is 0. There are two different reasons for this. If this block is singleton, so only contains one element, then because phi of aj is equal to 0, and if it has at least two elements, then it is 0 because of the vanishing of mixed cumulants. Because then it contains at least two arguments, but because neighboring elements are coming from different algebras, it must contain at least two elements coming from different algebras. So it's really a mixed cumulant. Okay, and since every non-crossing partition contains an interval block, for each pi, this term is equal to 0. So this continue here. So this is equal to 0. The phi of A1 up to AN, since each non-crossing partition contains an interval. And this one, this one, that's enough for example. Good. Okay, so you see this direction is fairly straightforward and simple. Good. Now the other direction, that's the crucial part of the proof. When it's important that we really have here a characterization of freeness, so that we can go back and forth. So we want to show if our variable or subalgebras are free, then all mixed cumulants vanish. I mean, the vanishing of mixed cumulants, in a sense there are much more mixed cumulants which have to vanish than I have situations where the moments are vanishing. Because the conditions are free. Good. Okay, so I have to see if elements are free, subalgebras are free, then mixed cumulants should vanish. And as I said before, if we would make here the same assumptions as for the moments, then this would be quite straightforward. So let us first check this. So assume, now not that we are in this weaker situation, but assume the situation which we have in the definition of freeness. centered and also ordinary. So phi of aj is equal to 0, and the neighbors are coming from different algebras. And then we can also somehow transfer what we know about phi to the kappas, now of course going the other way with the Möbius inversion of this. So then again, by more or less the same kind of argument as we did here, we can get the statement for the kappas. So then again, that we move on kappa n, the cumulant v1 up to the n. What is this? In terms of the moments, it's again summing over non-crossing partitions. And here I get the multiplicative contribution of the moment, so I get phi pi of a1 up to the n. And then I multiply this Möbius function, μ1 of pi, comma 1n. Yeah, and now we should see that at least in this situation, that we make quite strong assumptions on the a's, those guys are 0. Again, it's given by a sum over terms corresponding to pi, so it would be good to see that each of these terms is equal to 0. So we should see that each of those guys is equal to 0. Okay, but again, this here is a product of terms corresponding to the blocks of pi. And again, we have one interval, at least one interval partition there, and there I have a phi of neighboring elements. But then I'm exactly in the definition where Freeness tells me that phi of such a thing is equal to 0, because now I have, I'm not having a full string of a1 up to an, but only a substring interval, but still, of course, all phi's are 0, and they are all alternating, so phi applied to this is equal to 0. So this means for the interval block, I have one factor here which is 0. So this means this is always 0. So this pi contains interval block block V, and for this, the phi of the a's restricted to this V is equal to 0 by the definition of Freeness. Because now I have the strong conditions which I need on the a's for that this is equal to 0. Good. Okay, so you see, if I would have here this condition that the a's are centered and they are alternating, then going back and forth between moments and cumulants is just writing down the relation between them. One of them is the convolution of the other is the theta of the Möbius function, and then the condition goes from one side to the other, not just by induction, because you have it for one block. Okay, but the whole point is now that we want to weaken this. We want to see that the vanishing of mixed cumulants is also true if we have these weaker conditions. So what we have to do, we have to get totally rid of the assumption that the a's are centered. This doesn't show up there. And we also have to weaken this assumption of alternating. And getting rid of the assumption that they are centered, that's exactly what we can do, because we have seen, I have cumulants, where I have a 1 as an entry, this is 0. Which means we can actually shift our arguments by multiples of 1, which means we can center them without changing the value of the cumulant. Okay, so this means because of the fact our cumulants a1 up to an does not change its value if n is bigger than 2 if I center the variables. So this is the same as kappa n of, let's say, a1 minus 5 minus 1 and so on, an minus 5 times 1. Also this is the same if I have these two arguments. This was what we did last time. And why is this the case? Because cumulants are multilinear, so I multiply this out, I get one term which has all the a's. And this is of course this term. And then I have many other terms where at least one of the arguments is a multiple of 1. Okay, so I multiply, I can put it out. So I have the other terms, they all contain at least one as an argument, but we have seen that all those contributions are 0. So this means this here is this term plus many other terms which are all 0. Okay, so this means we can actually, on the level of cumulants, we can center our arguments without changing the cumulant. For n bigger than 2. Of course, for n equal to 1, of course, that's not true. But for the other ones, the ones where we're looking for mixed situations, we can center the guys. Of course, this is very different from moments. Right? If we center the situation for moments, then of course we get many other terms. That's exactly the problem if we use the definition of freeness for calculating mixed moments. We do this by centering, but then we get many terms which we have to control. If we do the same thing on the level of the cumulants, it's very easy. So this means we can center it. So we can assume actually that our A's are centered. Because instead of looking on this, we could look on this situation. But of course, the cumulant is the same. If you want to see that this is 0, it's enough to see that this is 0. Good. Okay, so this means we can get rid of the assumption that our guys are centered. So what we have now is that we are one step closer to what we really want. So namely now we know whenever I have a situation, I'm looking on the cumulant with at least 2 arguments, the A's are coming from subalgebras, and I still need that they are alternating. So I still have alternating, but I don't need any more that they are centered. And under this situation, we know, and we have seen now, that the corresponding cumulant is equal to 0. Good. Okay, but still, we want to get rid of this, or replace it by this condition that the guys are alternating. And of course, I mean, if I have a string of elements which are multiplying, and they are coming from subalgebras, but now I'm in a situation where not necessarily neighbors are coming from a different subalgebra. Of course, I mean, what can I do to go to a situation that's alternating? I just multiply the neighbors together, which are coming from the same algebra. So this means I can also write my non-alternating product as an alternating product, where now I have terms where each of them is a factor of some of the middle A's. And this, of course, is exactly the situation that you considered before, where we connected the cumulants of such situations. So that's the reason why this will be a very useful theory. Good. Okay, so in general, means now I'm really assuming a situation which I have in my theorem. I have elements, but not necessarily alternating. I can make it alternating. We multiply neighbors together to make them alternating. So this means that I'm writing my original product A1 up to AN of terms which are not necessarily alternating as a product of capital A's A1 up to AN. So the capital A's are just the product of neighbors which are coming from the same algebra. And of course, this n here will then be usually smaller than this here. You are really multiplying this. Okay, and so for these capital A's, I mean, they are still coming from some of the subalgebras. AJ is coming from some subalgebra. But in this case, I really have that they are different. So the one is different from 2. Different from Good. Okay, and now what we want to see is that actually the cumulant of those guys are equal to 0. And what we know already is that the cumulant of those guys are equal to 0. Because this is a situation which you already know. Okay, but we can also connect the cumulant of this with this. And hopefully this will be good enough. So, let's see. maybe we should also note, yeah, of course, I mean, if you want to see that the moments of these guys are equal to 0, of course, m should be bigger than 2, because we need mixed things. Yeah. Okay, but because we assume that the little a's are mixed, so they contain at least 2 different subalgebras. Of course, the 2 different subalgebras must also show up on this side, so I have here at least 2 terms. So m is bigger than 2. It's greater or equal to 2, because by assumption, A1 up to AN are mixed. So these 2 different subalgebras. Good. Okay, so this means we already know that for the capital A's, the cumulants are 0. So by m, A1 up to AM, this is equal to 0. From what we already know. But now we should connect the capital A's with the little a's. So, on the other hand, so we can also express the cumulants of A1 to AM. So the m's cumulant, of which we know that it is 0, we can also connect this with the cumulant of the little a's. So what was the formula? So I mean, capital A's are products of the little a's. So some here over numbers of partitions, but not over all of them, but only over those which satisfy this special condition, namely that the maximum of pi and the 0 n hat is equal to the maximal element in any single n. I mean, this was the image under this head mapping, and this head mapping, of course, contains information how we multiply. Good. And so what is this? And of course, if I'm summing over the pi which satisfies this condition, there's always one pi which does this, namely 1n. Okay, so the maximal pi satisfies this condition. So we get here in any case the term in which we are really interested. So namely, if I take the term kappa pi for pi equal to 1n, the little a's, we're doing so. Kappa pi if I take now pi equal to 1n, then I just get the kappa n of all the little a's. Kappa n, up to n. And then I have potentially also other terms which satisfy this condition, but are different from the 1n element. So I also have the terms, conditions, n, which satisfy this condition that the maximum of pi is 0 n hat is equal to 1n, but I should exclude the term which I already have here, which is the term 1 pi not be 1n. And I have here pi to an. Okay, now is the question, I mean, do we get anything here? Of course, the idea is we shouldn't get anything, because then this is 0. If this would not contribute, then this would be 0. That's what we want to see. So we better should see that actually this sum here is 0, which means that if we have pi's which satisfy this condition, then the contribution kappa pi is equal to 0. Or if we want something for which kappa pi is not equal to 0, then it cannot satisfy this condition. And so the kappa pi is of course again a product of smaller kappas for blocks. And now we also do induction, so we can assume that for smaller kappa n's we already know that mixed cumulants are equal to 0. So we do induction, and I mean all the blocks which are showing up here are smaller, they have length smaller than n. Because I mean there are at least 2 blocks. The situation where I only have 1 block of length n, this is covered here. In all the other situations, I have at least 2 blocks, and so each of the blocks must be smaller than n, which means by induction we can assume that for those I already know that mixed cumulants vanish. Which means that if I want this to be different from 0, that the blocks of pi can only connect elements from the same algebra. Because otherwise it would be mixed cumulant. So, next down. Induction. You can assume that the blocks pi connect all elements from the same subalgebra. We don't want mixed cumulants there, because by induction we know they are zero. Good. Okay, so this means this. But then, of course, we also have to consider this condition. So this tells us that my A's must be somehow connected via this or via this to the whole guy. Which means essentially I must connect elements A1 up to AN. All of them must be connected if I use this or this. So this condition, the maximum pi and 0m is equal to 1n. So this means that all elements must be connected via those two guys, via pi and 0m. Also in alternating way. We saw that if I want the maps of two elements, what I have to do, I mean, if I want to see that two elements are connected, I mean, I should find, it's not that I have to find directly a block either of pi or the other guy which connects them, but I mean, I must connect this via one of them with some other element, and this other element must be connected to something via one of the two, until in the end I'm reaching the two guys which I want. And if I want in the end 1n, this means any two must be connected by going over those two guys. So connecting via this and via this. Good. Okay, but you see, I mean, pi only connects guys which are in the same subalgebra. And of course, the sigma m hat also connects only guys in the same subalgebra, because the blocks of them are given by elements which are multiplied together, and those were elements from the same subalgebra. So this means this and this only connects elements from the same subalgebra. So if I want to connect any two guys by doing this, this means that any two guys must be in the same subalgebra, which means everything must be in the same algebra. But of course that's not compatible with our situation, because we know that we are looking on a mixed situation where I have at least two little a's which are coming from different algebra. So this gives us a contradiction. Or this means it's not possible to find a pi who satisfies this. The pi which satisfies this, and the other condition that it connects elements from the same subalgebra, which we can assume by induction. Okay, so via this, what this means, hence all in I must be in the same subalgebra. But this is a contradiction in the fact that m is greater or equal to 2. Which means to the fact that we have mixed guys. So we have at least 2. So this means actually there is no contributing pi in this subalgebra. So this means if I find something which satisfies this, then the kappa pi is equal to 0. So this means this whole sum here is equal to 0, and we just have that this is equal to this. So that's kappa n, A1 up to n. This guy here is actually the same as the kappa m of the capital A's. For those, we already knew that this is equal to 0. Okay, so essentially we have proved our statement, maybe up to the point that I used induction here on the length of n. Okay, we're doing induction, one should also start induction somewhere, so maybe we should check a small n. So let us also look on this. The smallest possible n is equal to 2 to get induction started. Consider n is equal to 2. Maybe there we should see directly. Okay, so what is this? So we're looking on kappa 2 of A1, A2. So there we have a mixed situation. So A1 and A2 are coming from different subalgebras, which are free, which means A1 and A2 are free. Okay, and of course, kappa 2, we know what this is, we can write this down explicitly. So this is 5 the product, so 2 minus the product of the 5s, minus 5 of A1 times 5 of A2. Okay, but now A1 and A2 are free, because they are coming from different subalgebras, and the subalgebras are free. So this means, of course, we know that this guy factorizes. Yeah, we know. Mixed moments in free algebras factorizes. So this here is actually just 5 A1 times 5 A2. Since A1 and A2 are mixed, that's our assumption. So this means those two elements really must come from different subalgebras. The subalgebras are free by our assumption. So this means that I have this factorization, and then you see this cancels away, and so we get 0. Okay, so this means that we have it for small n, and of course, if you like, you can also check it for any equal to 3, just maybe explicitly to see that if you have a situation A1, A2, A3, where let's say A1 and A3 are the same algebra, and A2 not, and then we know factorization rules for the moments. But you have to see that in the expression for the cumulants, all these factorizations in the end cancel all the way. They all go away. That's what this here is saying. And here's a very easy example, but of course for higher moments this is getting more and more complicated. Good. Okay. And so this is the crucial basic statement about free cumulants, how they characterize freeness, and this characterization is for subalgebras. So our definition of freeness was originally for subalgebras, but usually what we are really interested in are random variables, elements in our big algebra, and of course the freeness of the random variables is the same as the freeness of the algebras, the subalgebras which they generate. So of course this characterization here also tells us how we can decide whether random variables are free, but in a sense maybe it's not an optimal theorem, because if I want to check whether random variables are free, here in this theorem I have to look on arguments, mixed cumulants, where the a's here are in the algebra from our random variables. Okay, but what I would expect is to have a characterization which just uses the cumulants of our random variables, and this means I just want to put in the random variables as arguments, but not products of them, or something like this, or not elements from the algebra. Okay, and one can refine this here, again by using the formula for the product, to a characterization where I only have to check cumulants which involve really the cumulants of the random variables. So I want to write this down, but this actually is an assignment of the new exercise, or the new assignment. But this is important, because I mean, for random variables, you would have to check for all elements in the generated algebras. This would be quite tedious. Also, if we talk about random variables, we only want to look on the cumulants where they appear. So I'm writing down the statement, but you have to prove it in the next assignment. And of course, the main point is to get rid of products, or to reduce products just to single factors, and of course to use again the product formula for the cumulants. Good, so here's the statement. So a version of this, but for random variables. So then, non-probability space corresponding cumulants. again. Cumulants. And now I'm not considering subalgebras, but I consider random variables. Random variables, which are of course just elements in my big algebra A. So I consider these API in big algebra A for I for some index Z, and then I want to know whether those guys are free. And then we have this corresponding characterization as here. Then the following equivalent. First thing, of course, they are freely independent. AI. All guys I'm considering are freely independent. Which again is a definition in terms of moments. We are looking on elements coming from the subalgebras generated by them, which means I'm looking on polynomials in those guys. But now I want to characterize this by cumulants, but only looking on cumulants where all the arguments are just those A's. So I'm looking on the situation n greater than equal to 2, and then I'm looking on a mixed cumulant of them. This means I take just any arguments indexed by I, but I assume that that at least two different A's are involved. So this means again I have indices L and K between 1 and n, such that L is different from K. And in this situation, the kappa n, where I'm plugging in the A's with these arguments here, they are all zero. So kappa n of A1, A2, up to AN, this is equal to 0. So I mean, here the A's are really just my random variables. Of course, here I also have A's, but these A's were arbitrary elements in the algebra. So here on this side, if I would like to use this characterization here, I actually would have to plug in polynomials in the little A's. But here I'm saying I don't need polynomials, I just can take the random variables themselves. I just have to check what happens if I plug the A's there. And whenever I have a situation that if at least two different A's are showing up here, then this is equal to 0, then this really means that the guys are free. Good, okay, so but that's what you should prove in assignment. And of course it's clear, I mean, linearity, I mean, polynomials are sums of powers. The sums, of course, by multilinearity are not a problem, it's really powers. So that you also have to show that if you would have powers here, or you know that powers are equal to 0, or the other way around. If you know this, then you also have to see that you know it for powers. It's clear that you relate this by the formula for the cumulants. Good, okay, so any questions on this? Good. Then, maybe I want to go a little bit more in this direction by looking on cumulants of random variables. I mean, now we have defined those cumulants as very general objects, cumulant functionals, where we can plug in arbitrary arguments from our algebra. Okay, but usually we are interested in, let's say, one random variable, and then of course I'm just looking on moments of these random variables, which means phi applied to the power of this, or on the cumulant side, I'm just looking on cumulants where I plug in my random variable. Okay, and of course we know the relation between moments and cumulants is given by a nice combinatorial formula, where we have to sum over all non-crossing partitions. But I mean, this is nice from a conceptual point of view, but if you really want to do calculations, maybe it's not so useful, because I mean, the sum over a non-crossing partition, if n is a little bit bigger, then it's really a very huge sum. And if you don't see any structure there, or if you can do some kind of partial summation, it doesn't really tell you much. So now we want to go in this direction, that we want to translate this combinatorial description into a more analytic one, which can really be used for doing calculations. Okay, the first step, is that we essentially rewrite these combinatorial properties in terms of formal power series. And later on, we really will give those power series really more analytic structure. But even on this formal power series level, it's already very useful. So this is the mark. What we want to do. So this means now I just concentrate on one random variable. I really want to understand the relation between moments and cumulants better. Only for one random variable. So consider now a fixed random variable A in my algebra. Okay, and then I have moments. And these moments. So what are the moments? Moments I denote by m sub n. So this is my, let's say, my moment functional applied to arguments which are all a. So I'm applying a. Okay. But of course, I mean, the moment functional just multiplies the guys in x5. So this is nothing else than 5 of a to the n. So that's what we usually call the moments for all a. So we have the moments, and of course we have the cumulants. Corresponding thing where I'm plugging in the a's in the cumulant function. So let me call those guys kappa n. So kappa n is now just a number. It's not, before it was our multilinear functional, but now I just denote kappa n of a, comma a. So I take this functional and I'm plugging in all the arguments are now a. Okay, so those guys are now just sequences of numbers. The sequences of moments and the sequences of cumulants. Those are just sequences of numbers. And of course, we extend them in a multiplicative way to numbers which correspond to non-crossing partitions. So extend multiplicative functions on non-crossing partitions in the usual way. So by a non-crossing partition of n elements, then, so what is m pi and kappa pi? So this is just a product over m's or kappas corresponding to the blocks of my non-crossing partition. Because I mean my arguments are now just one random variable, I don't have to bother about which arguments are sitting at which position. So it's just a product. Also let's say my multiplicative function, I would say it's a function on partitions, but usually I'm with the subscript Fi, which is just a product over the blocks of I, and then I multiply the moments. Which moment do I take? I take the moment which has the number of elements in the block as subindex. And the same for kappa. Kappa sub pi, which is just a product over the blocks of pi and then kappa is this number of elements. Okay, so that's our relation between the moments and the cumulants, and of course abstractly this is just the convolution theta or the Möbius function. So and of course we have the relations. The kappa is given by from m by convolution with the Möbius function, or the other way around, which is equivalent, that m is given in terms of kappa by convolving it with the theta function. That was, this was definition of our cumulants, and now we did it very general by having arguments, but now if the arguments are all just one random variable, I mean we are just within the moments of the cumulants of this random variable. and it's just about a sequence of numbers. Yeah, okay, and so of course, so we have this, we know, if I have moments, this determines cumulants, and if I have cumulants, this determines moments in a very precise combinatorial way by formula summing over non-crossing partitions, and we have multiplicative contributions. But as I said, it would be much better, really for doing calculations, if you would have an analytic reformulation of this. Okay, and that's what can be done. Essentially, we can reformulate this connection between the moments and the cumulants into a relation between formal power series, where the coefficients in the formal power series are either the moments or the cumulants. And that's the following theorem. Use a full word for this. So it's really an equivalence. So we're saying we can describe this relation in an equivalent way in terms of corresponding formal power series. Okay, this has a priori nothing to do with moments and cumulants. It's just about two sequences of numbers which are related by this combinatorial description. Of course, I mean, for us those sequences of numbers will be moments and cumulants, so I will denote them in this way, but it's really independent of this background. It's just a combinatorial statement about two sequences of numbers which are related in a very combinatorial way, and this can be reformulated in a power series way. Okay, so this means let us consider two sequences of numbers, or maybe more generally they determine two multiplicative functions. Two multiplicative functions, which I call M and kappa. Those are functions A and C taking on complex values, which are determined via this, for this star. So this is a multiplicative extension. I'm giving numbers, either these numbers or these numbers, and then I make a multiplicative extension to a function on non-crossing partitions. Okay, so multiplicative functions determined star by the MNs, which are the value of my function on the maximal partition, 1n, and kappa n is kappa of 1n. For just saying, I mean, I have a sequence of numbers mn, and then I define a multiplicative function of non-crossing partitions in this way. I have a sequence of numbers kappa n, and I define a function on non-crossing partitions in this multiplicative way. Okay, so we have two such functions, and we want to check what does it mean that they are related in this way. Okay, and we want to reformulate this in a formal power series statement. So we also consider the formal power series. So consider moreover corresponding power series. So I take the power series in some indeterminate, let's say Z, and I take formal power series, so sum over powers of Z with some coefficients, and the coefficients are just those numbers. So I have one power series for the moment, so for this n, which is denoted by capital M, so M of Z is 1 plus the sum over n from 1 to infinity, then I have coefficient mn, and then I have Z to the n. And I do the same for the other guys, then I denote the power series by C of Z, so this is 1 plus, and again I take here the same kind of formal power series, but the coefficients are not determinants. Okay, now I want, so up to now I just have objects. I mean, I have on one side I have the M, and of course one capital M. On the other hand, I have the kappa, and I have the C. At the moment, those two multiplicative functions don't need to have anything to do with each other. But now I want to understand what does it mean if they are related exactly by this, in this way. What does it mean in particular in the relation between this and this? Okay, there's a characterization, so namely one can formulate things in equivalent way. So then, formulate equivalent. And of course, the first one is exactly this combinatorial relation between those two functions. So, the first statement is that M is the convolution of kappa with the zeta function. Or maybe, let me write it down again what this means. So this means that Mn is given by summing over all those partitions of n elements, and here I have kappa pi. This kappa pi is the product of the kappas corresponding to the blocks. Convolution with zeta function just means I'm summing over. Because the zeta function is this way. Or you can also write it the other way around, that you get the kappa n is the sum over this, and times the m pi, and then you also get the Newton's function. Oh, this is good. That's you know, also I don't to say this. Good. Okay, then the second one is that somehow one can do some kind of partial summation over this. So I want to write another relation between the m's and the kappas, but where I have done part of the summation here, and it's more a kind of recursive relation, which involves also the m on the other side, and which is somehow a step into this direction. So then I'm saying that this is equivalent that I can write mn also as a sum over s from 1 up to n, and then I'm summing over many indices in s many by 1 up to s. They all can take on values from 0 up to n minus s, but they have to satisfy the constraint that the sum of them 1 plus s plus s is equal to n, and here I get kappa s and times m by 1 times m by s. Okay, this looks complicated at the moment, but we will see. I mean, we get it very natural when we are proving it. Okay, so we can express mn in terms of smaller m's. I mean, the m's which appear here all are smaller than n and the kappa. So this is doing partial summation here. We will see. Okay. Better see how we get it instead of thinking too much. Okay, now the main statement is that actually from here it's very easy to get a statement on the power series, namely there we have that if I take the series for the cumulants and I'm putting in as arguments z times m of z, I'm getting f m of z. So I have here a functional relation between these power series. I'm plugging in here as argument this, and then I'm getting m. So m and c are somehow related. And this is somehow a reflection of this combinatorial state. And of course this is, I mean, this relates me to power series, and of course I can also do the other way around. So I mean, this tells me something is in some sense the inverse of something, and if I do the other way around, we can also write it in the form that m of z divided by c of z is equal to c of z. So instead of writing m in terms of c, we can also write c in terms of m. Okay, so that's the statement. I mean, this second part is just maybe going from 1 to 3. Right? It's an intermediate step. Maybe also interesting, but of course the main thing is the equivalence between this and this. Good, so let us prove this. And of course, I mean, yeah, essentially we go from here to here and then from here to here. And then I mean going back is essentially just observing that both this and both this determine uniquely the relation between moments and cumulants. And if you know one direction, then the other follows automatically. Okay, the main step where we really have to do something is from 1 to 2. So 1. So we have to understand what does it mean to sum over non-crossing partitions. 2. So we have to sum here over all non-crossing partitions, and we already had such situations where we were trying to count, let's say, all pairings or all non-crossing partitions, and usually you do this in a recursive way. And how do you do this? You choose the first block of a non-crossing partition. So the first block means the one which contains 1, and then you see what is left over. So for the first block, of course, you have some possibilities for choosing this, but if you have chosen this first block, then you are left with a situation which again is somehow a similar problem. Okay, so we have encoding an arbitrary non-crossing partition of n elements in this way that we say, okay, what is the first block, and then what are the remaining possibilities. So how does this look like? So we write a non-crossing partition of elements. Yeah, in the following way. I mean, so what do we want to do? So we have the first element, so we connect this, we have non-crossing partition, so this can be connected to a couple of elements. So it can be connected with elements here, and then there are possibly elements in between, and there are also something outside here. So the last guy is n. Okay, so we are choosing the first block, and so how can we specify this? We specify this by saying what is this, and first of all we can say how many elements does this block have. So let's say it has S elements, and then we can say what are the guys which we have here. But maybe it's nicer to encode it by saying how many elements do I have in between. So let's say I have here I1 elements in between. I1 can be 0, because it could be that this is the next guy. Okay, let's say here we have I2 elements in between, and so on. And then here we also, the last guys, the ones which we have outside, this is IS, if we have S elements here. Good. Okay, so we write the pi as the first block, B. Okay, and I mean the choice of the first block can be specified by saying what is S, how many elements does it have, and then how many elements do I have in between. If I specify those numbers, then I'm specifying the first block. Good. Okay, so I have the first block, and then I have to choose the other blocks, but now we are in the usual situation. If I'm fixing the block, then for the remaining points, I cannot connect any more points from here with these points from anywhere else, because I mean, otherwise I would get crossings. So this means the blocks which remain, they only can do, they can either connect some elements here, or some elements here, or some elements here, but not one of those groups. So this means I have now here different groups of points, and for each of them I have some blocks of pi which connect those points in a non-crossing way. But this means what I have here is nothing else than a non-crossing partition of so many points. So this means what I have here, the pi, consists of the first block, and then it consists of some blocks which connect here, but this is nothing else than a non-crossing partition pi1 of those points, and so on. And here, the blocks which I have for those are non-crossing partition of those guys. So this is pi s. Okay, so, and those pi's, so the first pi1, this is a non-crossing partition of I1 many points, and so on, up to pi s, this is a non-crossing partition of is many points. Okay, so this is just an encoding, but where you see we are using the recursive structure somehow of non-crossing partitions. I mean, choosing or creating a non-crossing partition means we create first one block, and then we are left with sub-problems of creating smaller non-crossing partitions for each of the elements sitting between the legs of the block. Okay, but this means we can write our sum over all non-crossing partition by using this recursive structure. So this means, so what I want is Mn. This is given by summing the non-crossing partitions in elements, and I have kappa pi. And now I encode pi with this information. So this sum here over all pi is now given by summing, okay, over the first block. And for the first block, I have the possibility of choosing the elements in the first block. So let me call this S. And so I can sum over all possibilities S going from 1 to n. The first block can contain any element 1 and n as number of elements. And then I have to choose non-crossing partitions here. And so I am summing over all possibilities for which I have how many elements I have here. So this is the sum over the i's. I have I1 up to is. They can take on the value 0, 1 up to n minus s. But of course I have a constraint. I mean, I have I1 many points here, I2 many points here. And then of course I also have the elements from the first block, which are as many. But of course all points together must give me the n points which I have. So this is this constraint, which of course we also you can see why how the sum arises there. So I have here I1 plus, so those plus is, those are all the points in between. And then I also need the points from the first block, which are as many, and all together this must give n. Good. Okay, and then if I have fixed this, so this means I have fixed the first block. The data choosing S and choosing I1 up to IS with this constraint really means I have chosen the first block. Okay, and then I have to choose the rest, and this is given by non-crossing partitions of the I1, the I2, and the IS. So I also have to sum over pi1, non-crossing partition of I1 many points, up to IS, which is a non-crossing partition of IS many points. Good. Okay, and then of course I need my kappa pi. And now of course the nice thing is kappa pi is a multiplicative object, so it decomposes into a product of things corresponding to the blocks, and this really goes nicely with this encoding. So a kappa pi is a product of the blocks, so we have one block, which is the first block, which has length s. For this we get a kappa s. So we have here kappa s. Then, of course, we have blocks which correspond to the blocks of pi 1. So in kappa pi, we have the kappas corresponding to the blocks which are sitting here, but this is of course nothing else than what kappa pi 1 is. Kappa pi 1 is the product of the blocks of the kappas corresponding to this block. So we have kappa pi 1 and so on, and then of course we also have the blocks of pi corresponding, which are connecting those guys here, which are given by pi s. The product of those kappas is just the kappa pi s. Also, you see that we can, because this kappa pi is a multiplicative object, it decomposes in a very nice multiplicative way according to this description of our pi in terms of the first block and then the union of some other blocks. But now you see that it's actually that now we are really back to our original problem for smaller number of points. So namely, this sum here over pi 1, this only affects this guy here. So you see, I can do this summation here, but if I'm summing all pi's over so many points, the cumulants, what do I get? I get the corresponding moment. So what I get here is the moment of I many points. So this here gives me m of I1. And in the same way, if I'm summing over this gives me m of is. And of course in between. So what I get here is the product of m of I1 times m of I2 times m of is. And so finally, you see what I have here is exactly what I'm claiming. So I have the sum s from 1 to n. Then I have the sum over all those i's here with these special conditions, and what is left over here is the kappa s. And then I get here, so you see I have done the partial summation. In this sum here I have done some of the summation. So I get here m of I1 times m of I2 times m of is. And that's what is claimed here. Okay. And now we are just writing down our power series. And of course with the coefficient, so I'm starting here, and then I'm plugging in this here and see how I get this one. So
So this structure here is really, you just have to write it down and then you see that you get the other formula. This is really the crucial observation to get to the power series distribution. Okay, so let's do this. 2 plus 3. So I'm starting with the power series for M. This is the step from 2 to 3. So I'm starting with M of Z. This is just by definition my power series. It's a sum of n from 1 to infinity. I have here an n. And I multiplied by Z to 1. Okay, now I'm plugging in for my mn, I'm plugging in my recursion formula. So, what I get here is 1. I still have this sum over n from 1 to infinity. And for mn, I'm plugging in this formula. So what do I have? I have the sum over s from 1 to n. Then I'm summing over the i's. I1, is. That's clear, but satisfying this constraint that 1 plus and so on, plus is, plus the sum is n minus s. Good. Okay, and then what is my contribution? I get the product of kappas and m's, and of course I multiply with z to the n. Okay, but now I want to distribute the sets to the corresponding quantities, and because of this constraint, you see that this fits very nicely. So then I can give, if I have a kappa s, because this asks for having a set to the s. So I give a set to the s and the kappa s, then I have an mi1. This probably would like to have a set to the power of 1. Let's give it to it, and up to the mis. This probably wants a set to the is. Okay, so I have now distributed sets, and this fits because I have a set to the I1 up to set to the is and a set to the s, and because I1 plus is plus s, this is equal to n. So actually the sets which I have distributed here actually is equal to set to the n. That's what I have here. Set to the n I just have written this way and distributed to guys. Good. Okay, and now you see, I mean, essentially what we have here now looks like the power series. I mean, the power series for M, and this looks like the power series for the kappa. Okay, so we should do sum. To get the power series of M, I should sum here over the I1. And you see, here the summation over I1 is restricted to some constraint, but actually, because we now take the power series in N, we are running over all N. You see, this constraint goes away. Because, I mean, the n itself doesn't show up here anymore. So the n now only tells me that we do this summation over all possible constraints. The n itself is gone. It's just encoded now in the i's and the s. And so this means the s, so if I'm running over all n, this means s a priori is now running from 1 to infinity. So this goes to infinity. So if I erase this sum over n, then I can go from 1 to infinity, and actually n minus s can now be anything, which means this constraint just goes away. I don't have to care about this. That's the usual crucial thing if you do on power series constraints. If you have your combinatorial relations for finite n, they have to satisfy complicated constraints which are hard to control. But then if you sum over all n, you're getting rid of these constraints, and now we just have here unrestricted summations over the i's. So this means the sum over I1 just shows up here, gives me just the sum over this, which gives the formal power series for n. And here I have it again. So you see what I have now here is just 1 plus, I have the sum S running from 1 to infinity. Here I have kappa S. Bracket, Z to the S, and then this guy here, this is just the sum over, let's say, Mi, Zi, I running from 0 to infinity. This is just the sum over I1. Then I get the same for the sum over I2 and the same for the sum over IS. I get this term here S times. So I actually get this to the power S. Good. Okay, but this sum here, of course, is just the generating function for the moment. So this is just the M of Z. So what I have here is nothing less than 1 plus the sum that's from 1 to infinity. I have here kappa S, and then as argument I have Z times M of Z to the power S. I have here Z to the S, and here I have M of Z to the S. And the coefficient is kappa S. And this is now the this is the power series for the C, but the argument is this guy here. Because I mean, C, its argument is the sum over kappa, and then the argument to the power S. Okay, instead of N, I have here S. We could also rename this to N. Then you see that this is now the argument. So what I have here is nothing else than the function C applied at the argument set times M of Z. Okay. And so you see you get this very nice, very compact. I mean, this is now a very compact, functional relation between those power series, which in a sense encodes the same information like this combinatorial. Right? It's telling me a relation between the coefficients in this power series. So this functional relation between the power series is equivalent to this combinatorial relation between these coefficients. And you should think about, I mean, of course, this combinatorial relation determines the m's in terms of the kappas, and you should also think that, I mean, this relation between the two power series also gives you a unique relation between the coefficients here and the coefficients here. So this means, because we have seen that this combinatorial relation is the relation between this, but it's also the other way around. So we actually, to prove going from here to here, is already done, because if you convince yourself that a relation like this gives you a unique relation between the moments of the cumulants. Okay, so let me notice here. So we go back to 1, but actually for this one should just observe that both 1 and also 3 determine a unique relation between the sequence of the m's and the sequence of the kappas. Okay, so if I know that 1 is a solution for the relation in 3, it must also be the other way around. So this gives also 3 is a solution for 1. Because there's only one solution. No? Good. Okay, and then maybe we should also 4. 4, of course, is just a formal playing around with this relation to bring it in this form. So we will let me do this. Okay, so how do I get from 3 to 4, let's say? again, I mean, both determine each other, so it's essentially enough to go one way. Of course, we can also go backwards. So assume that I know 3, and I want to see that I have 4. And for this, okay, let us do a change of the variables. So let W be set of M times Z. So the argument in the C, because I mean I want, of course, I want to see C of this. What is it expressed as M of something? Okay, so if I have this, then of course Z is what? Is W divided by M of Z, which is the same as W and M of Z by the first relation which we have is C of Z times M of Z. But Z times M of Z is our W. So this means it's W divided by C. Okay, so this means here I have to express W in terms of Z, but I can also do it the other way around to express Z in terms of W. Okay, now I just plug it in. So then I have C of W. So this is C of Z times M of Z. But I should now express this in terms of W's. So C of Z, M of Z, this is the same as M of Z. Right, that's our first relation, but Z I can now express as W divided by C. So this is M of W divided by C. Okay, so this is just making a change of variable in this way so that I can also express it the other way around. Good, okay, and now maybe I want to look on a few examples. I mean, really to see what can we do with this power series expansion? Does it really give us something non-trivial? And maybe the first thing is we should recover maybe the relation between moments and cumulants, let's say for a semicircle or also a croissant. So let us do two examples. And I mean, okay, for this, we won't get anything new because we already know. We know essentially what are the cumulants of a semicircle and we know what are the moments. But we want to see that this really fits with this. So let us consider the case of a semicircle. Consider the case of, let's say, a standard semicircle. Semicircle element. On the level of the cumulants, this is given by the fact that only the second cumulant is different from 0. It's 1, and all the others are 0. Also for a semicircle element, the kappas are just delta into 2. So kappa 2 is equal to 1, and all the other kappas are equal to 0. That's what we saw last time, and essentially we saw this because this really, if we then calculate the moments, this really counts the non-crossing pairings. But now maybe we want to see that we can also recover, if we start from this, say we have this sequence of numbers, which is just 0, 1, 0, 0, 0, 0, that then the corresponding moments here is given by the Catalan numbers. Because I'm counting the moments is given by the Catalan numbers. Okay, so what does this mean in this setting? So we start, so say we know the cumulants, namely the cumulants of a semicircle. So what is the corresponding C? In this sum here, we only have the term n equal to 2, because all the other kappas are equal to 0. So this means the C, which we have there, is just 1 plus, and then I just get Z squared. Because only kappa 2 is equal to there. And then what does this mean for the moments? Relation 3 here, so this here, this tells us now somehow how we should get from this information the generating function for the moments. Of course we know this should be the function which counts the Catalan numbers, but let's see whether we get it from here. So what is then this relation? So this gives then, so what is it? So we have m of z. This is now c applied to this argument, but c is this one. So c, this is 1 plus, and then z squared, and the argument is z times m of z, so we have to square this. So you see that we have here a quadratic essential equation. Okay, and we already in the assignment, we saw what is the generating function for the Catalan number. It satisfies some equation. And here, of course, because we are in a semicircular case, odd moments are 0. So this m of z is actually an even function. So this means actually it's a function of z squared. So maybe we should write m of z is a function of z squared. Because m of z, all its odd powers are 0, because its odd moments are 0. The odd moments vanish. So in order we can write it like this, so maybe we should write the equation instead for m for this function f. Because there we don't have these zeros, which we don't need. And then, if we rewrite this, so I'm plugging in for m of z, this is now f of z, so this is 1 plus, I have z squared times m of z squared, and m of z is f of z squared squared. Okay, so you see, I'm plugging in this here for m of z, I get this equation, and now of course, the argument here is z squared, so I rename this to z. So I'm writing this in terms of z. So what I have here is 1 plus, this is now z, I have f of z squared, this is equal to f of z. Okay, this was exactly the equation which gives you the generating function for the Catalan numbers. This was done in one of the assignments. So this equation, this is equation for the generating series of Catalan numbers. This was assignment 3, exercise 1. Okay, so you see, this here tells us something which you already know, namely that for a semicircle, if we start a semicircle on the side that we say the semicircle is determined by the fact that its cumulants are of the simple form that only the second order cumulant is 1, all the others are 0, then this tells us what the moments are. Namely, then the moments are the cumulants. Because so we have a very simple generating function for the cumulants. And if we rewrite this relation to the generating function for the moments, then we see that we have here actually the function for the Catalan numbers, which of course are the moments. And of course we have this shift by z squared, because the Catalan numbers are now just only the even moments. Okay, so we can do the same for the Poisson. We should also get the same formula, but of course now everywhere, because there we are counting non-crossing partitions all the time. Okay, so maybe next time I will then also do the free Poisson, but this is also something we know. But then maybe we should also check whether we can get something which we don't yet know, namely maybe if we can get some information about the Möbius function and non-crossing partitions. Up to now we only know there is a Möbius function, but we have no idea of any value of the Möbius function. But this information is also contained in this formula, because the Möbius function is of course somehow related with such relations. Good, but I think I will stop here and do this